This is the second video, thermal physics video. This is about the ideal gas equation. Now, temperature scales. If we were going to design a temperature scale, what would we need? We would need a quantity that varies with temperature. For example, it might be the level of some mercury in a capillary tube, or it might be the resistance of a metal, or it might be the pressure of a gas, or it might be the volume of a gas. Lots of different things you could use for a temperature scale. And we assume that this quantity varies linearly with temperature. We assume that the height of the mercury against temperature is a straight line. We have to make that assumption because without the thermometer we can't really test it. We also need two fixed points. A fixed point is a situation that happens at a certain temperature that we can use to define our scale. And we need two of them. For example, with the height of mercury in a sealed capillary tube, our lower fixed point we say is the freezing point of water at atmospheric pressure, and we call that 0. And then our upper fixed point is the boiling point of water at atmospheric pressure, and we call that 100. So our scale goes from 0 to 100, and we divide it up into 100, and that's basically the centigrade scale. Now, William Thomson, we know him better as Lord Kelvin, came up with a temperature scale based on an ideal gas. So this temperature scale is actually based on something that doesn't exist. And the quantity that we assume that varies linearly with temperature is PV. So we assume that PV is proportional to temperature. The reason for this was people were using lots and lots of different thermometers, and despite the fact that they all agreed with each other at the fixed points, they didn't necessarily agree. In fact, usually they didn't agree in between. Thermometers based on the pressure of gases and volumes of gases tended to agree with each other quite well. So Kelvin had the idea of coming up with this theoretical temperature scale. And as it's theoretical and it's based on an ideal gas, and ideal gases don't exist actually, then you can't fault it really. It's a scientific ideal temperature scale. The upper fixed point is the freezing point of water at atmospheric pressure. You don't actually need to know. It's called the triple point. It's when water vapor and ice can be in equilibrium, and it's at about 273 Kelvin. Not degrees Kelvin, just Kelvin. And then the lower fixed point is absolute 0. Okay, now for 1 mole of an ideal gas, if we're saying that PV is proportional to temperature, then PV equals a constant times temperature, and that constant is called the molar gas constant. And we can find a value for it experimentally. It's 8.31 joules per mole Kelvin. PV equals RT for 1 mole of an ideal gas. If we have more than 1 mole, then the equation becomes PV equals nRT. And this equation, not many equations have a name, but this one does. It's called the equation of state for an ideal gas. PV equals nRT. You must remember that if ever you use this equation, and a lot of our thermal equations, now the temperature is measured in Kelvin. I mean, this is the Kelvin scale. This is the ideal gas scale. So to get from Kelvin to degrees centigrade, or degrees centigrade to Kelvin, you just basically add or subtract 273. 273 Kelvin is 0 degrees centigrade. Here's a problem for you to do. A cylinder of volume 15 litres, so that's 15 times 10 to the minus 3 meters cubed, contains 500 moles of a gas at 20 degrees C. Calculate its pressure, work it out, and you should get, rearranging the gas equation, P is nRT over V, 500 moles, 8.31, 293 It has to be in Kelvin, remember, divided by the volume, and you should get 81.2 times 10 to the 6 Pascal. Now, another very useful equation, if PV equals a constant times T, then PV over T equals a constant. Therefore, if you have a gas, and let's say you heat it up or you squash it or whatever, if it's a fixed mass of gas, then P1 V1 over T1 equals P2 V2 over T2. Let's look at this problem here. A bicycle pump contains 400 centimeters cubed of air at 20 degrees C and 100 kilopascal. A boy puts his finger over one end, then squishes this air so that its volume becomes 100 centimeters cubed. Calculate the new pressure of the air, assuming the temperature doesn't change. And then part B, the temperature actually increases by 11 degrees centigrade. Calculate the pressure taking this into account. A very common part A, part B, short answer A-level question. So you can have a go at it now. So first of all, if T is constant, then it's just P1 V1 equals P2 V2. Rearranging that, we get P2 is 400 kilopascal. If the volume is a quarter, then the pressure is 4 times bigger. Once we take the temperature into account, then we just multiply by T2 over T1, and there's the two temperatures in Kelvin, and that brings the pressure up to 415 kilopascal.